Well, this is the second video of 4 wherein we'll discuss electrophilic aromatic substitution and nucleophilic aromatic substitution. But I kind of wanted to come back to this slide every time to remind us of the big picture. Now, one of the big pictures was that we have aromatic systems, whether we're attacking an electrophile or a nucleophile is attacking the benzene ring. And we'll have to have substitution reactions because we have aromatic systems, and if we just add the electrophile to the benzene ring here, we have to create an sp3 carbon, and we don't want to stay with that. So we saw in the EAS reaction, after the electrophile is attacked, some weak base had to come in and take a proton from the benzene ring. There were 2 steps in the EAS reaction: attack an electrophile, and we've introduced 3 so far. And then in the second step, we had to have a weak base attack a proton in the benzene ring. And we said we needed a catalyst because this is an aromatic system. Now we'll finish our discussion of EAS, the 2 last reactions to consider wherein we have a different electrophile. Then in the next 2 videos, we'll start considering multi-substituent effects just to close the story on EAS. And in the last video, we'll consider NAS, nucleophilic aromatic substitution. Again, still substitution being the key word here, because we have to reestablish aromaticity. So in nucleophilic aromatic substitution, the ring will be attacked, not the other way around. The ring is attacking. In this case, the ring will be attacked in the nucleophilic aromatic substitution, and we'll still have to substitute something off. Well, it looks like, as we look at the chlorine, that'd be a great leaving group. If we have something negative coming in, this would be a great negative going out. So let's finish our discussion of EAS, and we're going to look at just 2 more electrophiles: alkyl groups or alkyl cations and acylium cations. So alkylation of benzene, which is really just putting an R group on the benzene ring, a alkyl group on the benzene ring. We have to use a catalyst still, and in this case we're going to switch over in most cases to a Lewis acid. That is something that can accept the lone pair of a halogen or heteroatom. So we have, just like we did before, chlorine diving in on the aluminum center, metal center that's partially positive, has an empty p orbital. We can come in and fill that up with the chlorine, and like before, this chlorine would start to develop a positive charge as it started to put its lone pair on that aluminum, which starts to weaken this bond because he's very electronegative, or he becomes very electronegative and pulls on this carbon. So we'll come to that, but again, we're going to see a catalytic effect that changes the alkyl halides so that we can go through an alkylation of the benzene ring more easily. Because it is aromatic, we needed a catalyst. So let's go ahead and just review, or just talk about just a little bit of the general issues with alkylation, and we'll come back to this reaction. This is a very important type of reaction. Why? Because in the end, a carbon-carbon bond will be made. I want to note something else, that we can use, instead of a alkyl halide and Lewis acid, we can use an alkene with a Bronsted acid to generate a carbocation. An alkene, so let's just use isobutene. We can use that with a Bronsted acid, wherein we take the alkene, the pi bond, and attack the proton, and we can generate a carbocation this way, alkene with Bronsted acid. Some general features about the alkylation reactions is that the reaction can be difficult to stop after single substitution. This alkyl group, once on the benzene ring, can affect the benzene ring so that this is more electron rich. It's not much. It's not a significant or large redistribution of electrons within this sigma bond, but it's small. This carbon is sp2, and this carbon is sp3. So there is a slight donation back because this has more p or s character in the hybrid orbital reaching out to this carbon, which is reaching out with his sp3. It has more s character, so it tends to pull a little bit more electron density towards itself because it has the lower energy hybrid orbital. Alkyl groups in general are electron donating groups in an EAS reaction. Now let me ask the question of you. If it's electron donating, is it an activating group or a deactivating group in an EAS reaction? Electron donating, and we want to go hit an electrophile. Is it a good thing to have more electron density when you go try to hit something positive? Pretty simple question, I think, and fair. If I'm with electron density, extra electron density, because I have a donating group off of me, yes, I would be able to hit a positive charge more readily or more easily. So I would have an activated ring. So this can continue to add more alkyl groups preferentially over the unsubstituted benzene ring. That's why we can have a hard time stopping after single substitution, because the ring is more reactive. One last thing about alkylation of benzene. We do need to worry about, if we ever form a carbocation, rearrangement occurring. Now, I didn't have to worry about it here because I have, in the protonation by Markovnikov rule of this double bond, or pi bond more specifically, I have a tertiary carbocation. There would be no rearrangement. Let's consider this reaction up here to see if we would have rearrangement. So we're going to go ahead and go into the next slide wherein we give the detail for this reaction. So the mechanism for that reaction involves first the formation of a alkyl carbocation. So the salt needs to form, and again, we may not get a full salt, but it is practical to go ahead and draw out what that salt would look like, because we do have to consider rearrangement in most cases. So this is going to go ahead and be transferred to the aluminum, and I'm going to take these electrons with it, because he's going to develop a very significant positive charge as he binds, and even though this arrow may come after subsequent, after some time after which this is bonded to the aluminum, I'm going to draw this together so that we can get right to the salt. The salt would look something like this then. We would have a positive charge left here, we of course would have a negative charge on the aluminum since he's gaining electrons, and we've gained one more chlorine. So we have the salt formed. This is our salt. And we have increased the reactivity of our electrophile. We have increased it. So this is now more reactive than the alkyl halide. This had a partial positive charge, but now it's a full positive. So that helps again, because the benzene ring is aromatic. We can have a hard time breaking aromaticity. We have to use sometimes a catalyst. Alright, so now we're ready to go through our EAS reaction. Attack an electrophile with the aromatic ring and go towards substitution. So we know that. So we're going to, oh, and I forgot, we need to consider rearrangement. That's a secondary. Before this can come in, does this rearrange? It's a secondary carbocation next to primaries. So no, we can come in where it sits without rearrangement and start our reaction. So what do we go to? Well, the thing we always went to in EAS was the sigma complex. We go to that non-aromatic intermediate that's formed in every EAS reaction. We just have a different electrophile. So let's put that at the 12 o'clock position. So it's just in a different electrophile going to be attached here. We still have a proton there. There's a proton there that's going to have to come off. Where's the positive charge going to be? Well, we're using this pi electron density, so this guy is left in the cold. So we have this And of course I guess the salt would just come along with it, the anion. And that's going to become important in this next step. So I guess I've already drawn it here, but I'll leave it here and we'll cross that out. So that weak base, this is again not in aqueous conditions. We can't use Lewis acids in aqueous conditions. That weak base will come in and grab the proton off the carbon that's sp3 hybridized. We heard that in the last video. If you want to know how to end an EAS, make sure you attack the electrophile with the benzene ring and create a sigma complex, or what we call the cyclohexadienyl cation. But then we have to attack the proton that's on the carbon that's sp3 hybridized and bring those sigma electrons back to a pi bond. And we're done. We generate HCl. We regenerate our Lewis acid catalyst. And we are done. Now again, this could go on to react. We do see in many cases disubstitution of the benzene ring because this is more reactive than the initial benzene ring. But that just shows us monosubstitution, the mechanism for such. Let's go ahead and go on to the next one. I guess acylation, and again, remember the notes. We can have disubstitution of the benzene ring, not just monosubstitution, and we do have to remember carbocation rearrangement. If we have a secondary next to a tertiary or quaternary, this would be a secondary next to a tertiary carbon, we have to consider rearrangement. So make sure before you attack that carbocation formed through the Lewis acid, make sure you consider rearrangement before the benzene ring can come in. Alright, acylation, acyl groups. We're going to just think of a carbonyl, and we're going to have some sort of R group or hydrogen or something off of this carbonyl, and we're going to attach this to the benzene ring. Acylation of benzene. We're going to use a Lewis acid again, and we're still going to have the chlorine here, considering that as interacting with that aluminum so it gets torn off, and we make the acylium cation. I'm going to draw it with an odd angle because it's really resonance stabilized. So it's a positive charge on this carbon because we're breaking off that chlorine and it's going to the aluminum. We would have AlCl4- just as we did before. So we would have our salt. And again, it's very good if you see the Lewis acid and the acyl halide or alkyl halide to go ahead and draw the salt so it becomes very clear what your electrophile is. So we have in this case what's called an acylium cation. Acylium cation. I'll just put ion. This would be what we consider as formed between the Lewis acid and the acyl halide. And I'm not going to go through the full mechanism on this reaction, but we can say that this ring attacks the new electrophile and we tear a proton off of that carbon that was attached to the electrophile to reestablish aromaticity, just like we did before. So there's nothing new here except a new electrophile. There are a couple things though that are different in comparison to the alkylation of benzene. We do not have a rearrangement. This cation is stabilized by the oxygen through resonance, and it's not a good thing in most cases to move away from resonance. So we leave it right here. The positive charge is attacked right here. So no rearrangement. And unlike alkylation, no further reaction to diacylation occurs. Why? Well, I think we can figure this out because we said if we want this ring to go again through an EAS, it has to be rich with electron density. This has to be a donating group. Well, this whole thing is not a donating group. It's an electron withdrawing group. It's electron withdrawing. This whole group is electron withdrawing. And we know that because we can see how inductively and by resonance this group would interact with the ring. This carbon is partially positive, made so because of the oxygen's pull on it through the pi bond and the sigma bond. So it's partially positive. And I know you might say, well, there's no difference in its hybridizations, sp2 to sp2. And we'd said on the last slide with alkylation, if you have a little more sp2 character in someone else's sp3, you pull from that sp3 atom if everything else is the same atoms. But these are not the same. They're both carbons, but he is very partially positive. So he becomes more electronegative. I hurt, you hurt. If I'm poor, I desire to be richer in a greater way. So he pulls on that carbon inductively. But we also can draw a resonance form where this oxygen pulls pi electrons up towards itself, and these pi electrons respond. So in both IE, and this will be our next video, and RE, the substituents effect on the ring is such that we pull electron density out through both inductive effect and resonance effect. This ring becomes electron poor. Don't say that it's not that it has no electron density and can't go through an EAS reaction, but it gets very, very hard, and it's very, very unfavorable for this ring to go through another reaction compared to this ring. This one still has more the electron density it started with. This one has less. So this can go through EAS reaction faster than our substituted ring. Our acyl group on the ring deactivates it. So we don't see, because this acyl group is electron withdrawing, we don't see disubstitution. One more thing. The Lewis acid that we use in acylation cannot be set to just catalytic amounts. Because it tends to bind the lone pairs in this carbonyl after the reaction, we tend to need to use an equivalent amount of this. Equivalent, meaning 1 mole, 1 mole, and 1 mole. And at the end of the acylation reactions, we use a water workup to wash that Lewis acid away. All right, well that's it. Those are our two new electrophiles. The acyl group through an acylium cation and through the carbocation from an alkyl halide. We have two types of electrophiles. Know the difference. Again, the alkylation, we can have disubstitution. Acylation, only monosubstitution is favored. And then carbocation rearrangement for alkylation, but no carbocation rearrangement for acylation. All right. Just as sort of an additional number of, I know reactions, sometimes you feel like you're overwhelmed. And in OChem 2, if you're overwhelmed, it might be that you're memorizing just disparate facts about polar reactions instead of making sense of polar reactions. So for example, when we look at the mechanism for that alkylation reaction, I hope this made sense. If it doesn't, you probably want to go back and review some videos on just basics of polar reactions. Electron rich likes electron poor. They tend to get together. So polar reactions, we have, I think, hopefully a sense of what makes sense and a sense of what to expect. But there are some reactions along the way in these videos that I'll be introducing where you simply are told, just know these reactions, and we'll try to catch up at some point to the logic behind them. And these reactions I'm going to leave till towards the end of my presentations to discuss. Oxidation reactions and reduction reactions, we're going to discuss all of them in one video. But for now, I'd like to just introduce what you need to know as reagents and what products are formed for 3 reactions, 2 oxidation reactions and I guess 4 reactions, 2 oxidations and 2 reduction reactions. Just recognizing reagents and knowing what products are formed. So no mechanistic detail on this slide. Just please know that when you have KMnO4, potassium permanganate, with water and you have an alkyl group off the benzene ring that has at least one CH bond, so one carbon-hydrogen bond involving this benzylic carbon next to the benzene ring. If I have at least one CH bond, so it could be an ethyl, isopropyl group, ethyl group, methyl group, N-propyl group, as long as I have one CH bond involving this carbon within the alkyl group, I can add KMnO4 with water in a first reaction and work up with acid in a second reaction to make carboxylic acid. So please just recognize that we would form carboxylic acid off the benzene ring, right off the benzene ring. if we have any alkyl group having a CH bond involving this benzylic carbon. So primary position carbon here, secondary carbon, tertiary carbon. Of course, if it was quaternary, bonded to 4 carbons, we would not have a CH bond here, and there would be no reaction. Now also please know that we can use, in place of that, we can use sodium dichromate with acid and generate the same product. So these can be used interchangeably. This can also be, so you notice something interesting, the oxidizing agents usually have a lot of oxygens. That's no maybe small wonder. But oxidizing agents usually have a lot of oxygens. Not always, but you can kind of say, oh, well, maybe that's an oxidizing agent. KMNO4, potassium permanganate, sodium dichromate, they have a lot of oxygens, and maybe that's an oxidizing agent. So that's 2 oxidation reactions that I'd ask that you just memorize for now. And then carbonyls can be reduced to CH2 groups using 2 types of reactions. One's a dissolving metal reduction, and the other one's more of a polar reaction. The Clemenson reduction, just please recognize this as the reagents for the Clemenson reduction. Zinc with mercury amalgam and some sort of acid, HCl here. Or the Wolff-Kishner reduction, hydrazine, H2NNH2, just an organic reagent, and KOH. Please recognize those as needed for a Wolff-Kishner reduction. Well, that's it. Bye-bye.